Thank you for watching my videos. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem that appeared in the CSIR National Eligibility Test held in the month of December 2023. The question is from the section Real Analysis, and it is related to the uniform convergence of a given sequence of functions. The question is placed in part C, which is a multiple select question. There can be more than one answer. It carries 4.75 marks. The question ID is 704065. Right. The given question is, let Fn be a sequence of functions defined on closed and bounded interval 0, 1 by Fnx is equal to x power n log of 1 plus root x by 2. Which of the following statements are true? We are given four options. Option 1. The sequence Fn converges pointwise on the closed interval 0 to 1. Option 2. The sequence Fn converges uniformly on compact subsets of the closed 0 open 1 interval, but not on the closed 0 open 1 interval. Option 3. The sequence Fn converges uniformly on the closed 0 open 1 interval, but not the closed interval 0 to 1. Option 4. The sequence Fn converges uniformly on the closed interval 0 to 1. So the question is basically talking about the pointwise and uniform convergence of the given sequence of functions. Let's now discuss the solution of the problem in detail. We have the sequence Fn n is equal to 1 to infinity of functions defined on the closed and bounded interval 0 to 1, where Fnx is given by x power n into logarithm of log of 1 plus root x by 2, where x belongs to the closed interval 0 to 1. Agreed. Let us take up the options one by one. Option 1. The sequence Fn converges pointwise on 0 to 1. Note that Fn 0 in Fnx substitute 0 for x. So Fn 0 will be 0 and true for all n. Therefore, limit n tends to infinity of Fn 0 is 0. If you substitute 1 for x, then Fn 1 is also 0. Therefore, limit n tends to infinity of Fn 1 is 0. So, for 0 and 1, it converges pointwise to a 0 function. So now we have to consider x belongs to the open interval 0 to 1. Then this implies 0 less than root x less than 1. Adding 1 throughout, you will get 1 less than 1 plus root x less than 2. Dividing throughout by 2, we get 1 by 2 less than 1 plus root x by 2 less than 1. Taking the logarithms throughout. Yes, the inequalities will not get disturbed because the logarithm function is an increasing function. So log of 1 by 2 less than log of 1 plus root x by 2 less than log 1 is 0. So this is true for all x belongs to the open interval 0 to 1. So it says that it is a bounded function. Right. Now limit n tends to infinity of x to the power of n. Logarithm of 1 plus root x by 2 is equal to 0. Where are we? We are in x belongs to the open interval 0 to 1. So when x belongs to the open interval 0 to 1, limit n tends to infinity of x to the power of n is 0. Right? For all x belongs to 0 to 1, the log of 1 plus root x by 2, which we have already seen that it is a bounded function. Therefore, limit n tends to infinity of x power n logarithm of 1 plus root x by 2 is 0. So, f and x converges pointwise on the closed interval 0 to 1 to a limit function f of x, where f of x is 0 for all x belongs to 0 to 1. For all x belongs to the open closed interval 0 to 1, limit n tends to infinity of x to the power of n into logarithm of 1 plus root x by 2 is 0, that is fx. That is, limiting function is f. So f of x is 0 for all x belongs to 0 to 1, that is the limiting function. So the sequence fn converges to f pointwise on 0 to 1, therefore option 1 is true. Agreed. We move to the next slide where we will consider option 4, fn converges uniformly on the closed interval 0 to 1. Is it so? So we have already seen the sequence fn converges to f pointwise on the closed interval 0 to 1, where the limiting function is f of x is equal to 0 for all x belongs to 0 to 1. Right. Now, we compute mn, that is equal to supremum of mod fnx minus fx, where the supremum is taken over x belongs to the closed interval 0 to 1, and that will be the supremum of mod fnx, where x belongs to 0 to 1, because f of x is 0 for all x belongs to 0 to 1. What is the idea? The idea is that we take this and show if mn tends to 0 as n tends to infinity, then we use the theorem that the sequence fn converges uniformly if and only if mn tends to 0 as n tends to infinity. That's the idea behind it. So now, note that fnx is continuous. Yeah, how the fnx is? Fnx is x power n logarithm. X belongs to 0 to 1. So the product of two continuous functions is continuous. Mod also is also continuous. Agreed. Agreed. And it is continuous on the closed and bounded interval 0 to 1. So it's continuous on the closed and bounded interval 0 to 1. Therefore, it attains supremum at some point c belongs to the interval, closed and bounded interval 0 to 1. Yes. Yes. Thus, mn, the supremum of x belongs to the closed interval 0 to 1, mod fnx is mod fnc, that is modulus of c power n into 1 logarithm of 1 plus root c by 2. Agreed. Now we are asking a question whether the supremum attains at x is equal to 1. That is, can c be 1? That's the question. We claim c is not 1. If you suppose c is 1, then fn1 mod of Fn1 is mod of 1 to the power of n logarithm of 1 plus root of 1 by 2, that is log of 2 by 2, that is log of 1 is 0. It is 0. It is 0. Yeah. That means at c is equal to 1, mod Fn1 is 0. And note that if you take c is equal to 1 by 4, then mod of Fn1 by 4 is, for c you substitute 1 by 4, mod of 1 by 4 to the power, mod of 1 by 4 to the power of n into logarithm of 1 plus under the square root of 1 plus under the square root of 1 by 4 whole by 2. This is mod of 1 by 4 to the power of n into logarithm of 3 by 4 modulus is greater than 0. So at some point 1 by 4, the value mod of that is greater than 0. At c is equal to 1, it is 0. So therefore the supremum is not attained at c is equal to 1 because the positive values are there. At c is equal to 1, it takes 0 value. So this shows that the supremum is not attained at c is equal to 1. Therefore, c belongs to the interval closed 0, open 1. Open 1. So now limit n tends to infinity of mn is limit n tends to infinity of c power n. Yes, c power n will come out of the modulus because it is 0 or positive. So c power n into logarithm mod of logarithm of 1 plus root c by 2. This is a fixed point. This is fixed. This is fixed. And therefore limit n tends to c power n is 0. Why? Because c belongs to the closed 0 and open 1. When c is 0, is anyway 0. When c belongs to the open interval 0 to 1, limit n tends to c power n is 0. So now we recall that mn tends to 0 as n tends to infinity if and only if the sequence of functions converges uniformly on the closed and bounded interval 0 to 1. Therefore, the sequence fn converges to f uniformly on the closed and bounded interval 0 to 1. Thus, our option 4 is true. We move to the next slide for the discussion of the remaining options. Yes, we have already seen that our sequence converges pointwise and our sequence converges uniformly on the closed and bounded interval 0 to 1. Option 2 says the sequence fn converges uniformly on compact subsets of the closed 0 open 1 but not on closed 0 open 1. Now we have fn converges uniformly on 0 to 1. Therefore, fn converges uniformly on every subset of the closed and bounded interval 0 to 1. And the closed 0 open 1 is one of the subsets of the closed and bounded interval 0 to 1. Therefore, it should also be convergent there. So fn converges to f uniformly on the closed 0 and open 1 interval. Therefore, option 2 is not true. Call on option 3. Fn converges uniformly on the closed 0 open 1 interval but not the closed and bounded interval 0 to 1. But we have seen that Fn converges uniformly on the closed and bounded interval 0 to 1. Therefore, option 3 is not true. Right. The answer to this question is options 1 and 4. Right. So the answer to this question is option 1 and 4. We make a remark here that the uniform convergence of the given sequence on the closed and bounded interval 0 to 1 can be shown by using another theorem called Dini's theorem. Dini's theorem. So the uniform convergence of this sequence Fn can also be proved using Dini's theorem. So you can also use Dini's theorem. You try out. That can also be done. Agreed. That is the detailed discussion of the solution of the given problem from real analysis, which is related to the sequence of given functions and their pointwise and uniform convergence. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Thank you.